June 6, 1944, 0630 hours. While thousands of Allied soldiers stormed the beaches of Normandy under withering German fire, a different invasion was quietly underway beneath the waves of the English Channel. Ships were laying something that looked like enormous steel cables across the seafloor, unreeling them mile after mile from massive drums mounted on their decks. To any observer, they appeared to be telephone cables or electrical lines, critical communications infrastructure for the invasion. They were not cables, they were pipes, and they were about to solve one of the most critical logistical challenges in military history. Operation Overlord, the invasion of Normandy, required moving the largest military force ever assembled across water and sustaining it indefinitely on hostile shores. The numbers were staggering. 156,000 troops on D-Day alone, eventually growing to over 2 million men, with thousands of tanks, trucks, aircraft, and artillery pieces. Every one of these vehicles consumed fuel at prodigious rates. A single Sherman tank burned approximately 60 gallons of gasoline per 100 miles. Multiply that by thousands of vehicles, add aircraft fuel consumption, generator fuel, and the myriad other petroleum needs of a modern mechanized army, and the result was a logistical nightmare. Allied planners calculated that the invasion force would require 1 million gallons of fuel per day initially, rising to over 3 million gallons daily as operations expanded. Traditional supply methods, tanker ships unloading into smaller vessels, then to trucks, then to forward units, were too slow, too vulnerable to German attack, and completely inadequate for the scale of operations planned. The solution was unprecedented. Build a pipeline under the English Channel. Pump fuel directly from Britain to France, bypassing ships and ports entirely. Create an underwater supply line that German forces couldn't interdict, that didn't require escort vessels, that could deliver fuel continuously regardless of weather or enemy action. The project was codenamed PLUTO, Pipeline Under the Ocean. It was one of World War II's most ambitious engineering achievements, a technological marvel that combined innovative material science, daring construction techniques, and improvisational genius. Without it, the liberation of Western Europe might have stalled on the beaches of Normandy, starved of the fuel that kept armies moving. This is the story of the pipeline that followed the army, how British and American engineers built the world's first undersea fuel pipeline, how they solved problems nobody had faced before, and how their achievement kept the Allied advance supplied with the petroleum lifeblood of mechanized warfare. When Allied planners began serious preparations for invading France in 1942, they faced an unpleasant arithmetic problem. Moving armies required fuel. Moving fuel required ships. But ships were exactly what the Allies didn't have enough of. The Battle of the Atlantic was consuming merchant vessels faster than shipyards could replace them. German U-boats were sinking hundreds of thousands of tons of shipping monthly. Every tanker sent to supply invasion forces was a tanker unavailable for other critical missions, supplying Britain itself, supporting operations in the Mediterranean, providing fuel for the Pacific theater. Even if enough tankers existed, ports were a bottleneck. The Allies couldn't simply sail tankers to Normandy. German coastal defenses made that suicidal. Instead, fuel needed to be unloaded at captured ports, then distributed inland. But ports were obvious targets. The Germans could bomb them, shell them, or demolish them during retreat. Cherbourg, the nearest major port to the invasion beaches, wouldn't be captured until late June and wouldn't be operational until months later due to German demolitions. The alternative was unloading fuel over beaches using smaller craft. This was desperately inefficient. Tankers anchored offshore, transferring fuel to landing craft, which ferried it to beaches, where it was pumped into temporary storage, then loaded onto trucks for distribution. Each transfer consumed time, required personnel, and introduced opportunities for loss, contamination, or enemy interdiction. Worse, Beach operations depended on weather. The channel is notoriously stormy. Bad weather could halt fuel delivery for days, leaving armies immobilized. The Great Storm of June 19–22, 1944 demonstrated this vulnerability. It destroyed the American Mulberry Harbor at Omaha Beach and severely damaged the British harbor at Arromanches, halting supply operations for days. Allied logistics officers calculated that traditional methods could supply perhaps 400,000 gallons of fuel daily across the beaches, less than half of projected requirements. The gap between what armies needed and what traditional logistics could provide threatened to strangle the invasion before it began. In early 1942, Geoffrey Lloyd, Britain's Secretary for Petroleum, convened a meeting of oil company executives and engineers. The question posed was simple. Could fuel be piped under the English Channel? The experts' initial answer was equally simple. Probably not. No pipeline had ever been laid underwater at such depths or distances. The channel's narrowest point, the Strait of Dover, was 21 miles wide with depths exceeding 150 feet. Normandy beaches were farther. The planned pipelines would need to stretch 70 to 80 miles, crossing waters over 300 feet deep in places, dealing with strong currents, rocky seafloors, and the remains of countless shipwrecks. The pipe needed to be flexible enough to coil onto drums for transport and laying, yet strong enough to withstand water pressure at 300-foot depths and internal pressure from pumped fuel. It needed to resist corrosion from seawater, remain intact if dragged across rocky seafloors, and continue functioning if damaged by anchors, mines, or deliberate German attack. No existing pipeline technology met these requirements. Standard steel pipe was too rigid. It couldn't be coiled and uncoiled without breaking. Flexible hoses lacked the strength for deep water installation. Welded pipe sections were impractical. Laying 80 miles of pipe by welding sections together underwater was impossible with 1940s technology. The solution required inventing entirely new materials and construction methods. Two parallel development programs emerged. The first, led by engineer Arthur Hartley and Siemens Brothers Cable Company, developed what became known as HAIS pipe, Hartley Anglo-Iranian Siemens. This used lead pipe reinforced with steel wire, similar in construction to undersea telegraph cables. The lead provided flexibility and corrosion resistance. Steel wire wound around the lead gave it tensile strength. An outer covering of steel tape protected against abrasion. HAIS pipe was 3 inches in diameter, small but enough to deliver substantial fuel volumes when pumped at high pressure. The pipe could be manufactured in continuous lengths, coiled onto massive drums called conundrums, CONUNDRUMS, 30 feet in diameter and containing 25 miles of pipe. These drums would be towed across the channel, the pipe playing out behind them as they went. Both systems required solving subsidiary problems. How do you pump gasoline 80 miles through a 3-inch pipe? Standard pumps couldn't generate enough pressure. Engineers developed new pump designs capable of pushing fuel through the pipeline at pressures exceeding 1,500 pounds per square inch, far beyond normal pipeline pressures. How do you prevent fuel from overheating under pressure? Compression generates heat, and gasoline becomes dangerous when hot. The solution involved carefully controlled pressure stages and cooling systems at pump stations. How do you detect leaks in a pipeline lying on the ocean floor? Engineers couldn't inspect it visually or walk along it checking for problems. They developed pressure monitoring systems that could detect minute pressure drops indicating leaks, and flow meters that tracked exactly how much fuel entered the pipeline versus how much emerged at the far end. How do you protect the pipeline from ship's anchors, German mines, or deliberate German attack? Armor was too heavy. The solution was multiplicity. Lay several parallel pipelines so damage to one wouldn't halt fuel flow. Also, route them through areas where ships were unlikely to anchor and keep their exact locations secret even from most Allied forces.
PLUTO development occurred under extreme secrecy. Churchill personally approved the project in 1942, insisting that knowledge be restricted to essential personnel. The cover story was that Siemens Brothers was developing improved underwater telephone cables for military communications. Engineers working on PLUTO components often didn't know what they were building. Pump manufacturers thought they were making equipment for oil fields. Pipe fabricators believed they were producing components for petroleum installations in Britain. Only core teams knew the complete picture. The conundrum drums, absolutely massive structures that couldn't be hidden, were explained as equipment for artificial harbors, mulberries. Since mulberry construction was itself secret, this cover story worked perfectly. Workers building conundrums assumed they were fabricating components for harbor construction, not pipeline deployment equipment. Testing occurred under cover of darkness at remote locations. Experimental pipe sections were laid across rivers and estuaries, tested, recovered, and modified based on results. Engineers learned that currents could whip pipe sections violently during laying, that seafloor rocks could pierce protective coatings, and that tidal forces created stresses nobody had anticipated. Each problem generated solutions. Pipe coatings were reinforced. Laying procedures were modified to account for currents. Route surveys became more detailed, avoiding rocky areas when possible. The learning curve was steep, but there was no reference book to consult. Nobody had done this before. By early 1944, PLUTO was ready for operational deployment. Manufacturing facilities had produced over 1,000 miles of HAYS pipe. Conundrum drums held hundreds more miles of conventional pipe. Pump stations were constructed on the Isle of Wight and at Dungeness, disguised as ordinary petroleum installations. Ships were modified for pipe-laying operations, their specialized equipment hidden below decks. The stage was set for the most ambitious pipeline project ever attempted.
PLUTO pipeline laying began on June 8, 1944, D-Day +2. The first line to be laid was a trial run, a short HAIS pipeline across the Strait of Dover from Dungeness to Boulogne. But Boulogne remained in German hands, so this line couldn't be activated immediately. The critical pipelines ran from Shanklin, Isle of Wight, to Cherbourg on the Cotentin Peninsula, approximately 70 miles across open channel waters. HMS Latimer, a former commercial vessel converted to a cable-laying ship, carried the first conundrum drum loaded with HAIS pipe. Escorted by minesweepers and protected by fighter cover, she steamed across the channel at precisely controlled speed, the pipe unreeling from the massive drum mounted on her stern. The laying operation was delicate and dangerous. If the ship moved too fast, the pipe would stretch and potentially break. Too slow, and it would pile up on the seafloor in tangled coils. Currents pushed the ship off course, requiring constant corrections. German shore batteries occasionally shelled the operation, forcing temporary halts while vessels maneuvered clear. The pipe needed to reach the seafloor without excessive tension. Engineers calculated the exact relationship between ship speed, drum rotation, and water depth to achieve proper pipeline tension. Too much tension would stretch the pipe beyond its elastic limit. Too little would cause slack that currents could tangle. Weather was both enemy and ally. Calm seas made laying easier, but left vessels vulnerable to air attack. Rough seas hid operations, but made precise pipe deployment nearly impossible. Operations proceeded in windows of acceptable weather, working around storms and German interference. The first pipeline reached Cherbourg on August 22, 1944, 11 weeks after D-Day. By then, American forces had captured Cherbourg, though the port was still being cleared of German demolitions. Engineers immediately began connecting the pipeline to temporary storage facilities and distribution networks. On August 23, pumps on the Isle of Wight activated. Fuel began flowing through PLUTO for the first time operationally.
The pressure gauges climbed as gasoline traveled beneath the channel, pushed by pumps generating pressures that would have exploded conventional pipelines. Engineers monitored anxiously, looking for leaks or failures. The pressure held. Fuel emerged at Cherbourg at design flow rates. PLUTO worked.
One pipeline was insufficient for Allied needs. As operations expanded, additional lines were laid rapidly. By September 1944, 4 HAIS pipelines connected the Isle of Wight to Cherbourg. By October, 2 more connected Dungeness to Boulogne, now in Allied hands. By November, additional lines were being laid to Calais. Eventually, 21 pipelines were laid across the channel, 17 HAIS lines and 4 lines using the conventional pipe-on-drum system. Total pipeline length exceeded 700 miles. The network could deliver over 1 million gallons of fuel daily when operating at capacity. The pipeline network expanded as Allied armies advanced. Engineers laid pipelines following the Army's route, across France, into Belgium, eventually into Germany itself. By war's end, over 3,000 miles of pipeline had been laid across Europe, much of it using techniques and materials developed for PLUTO. This terrestrial pipeline network, sometimes called the European Pipeline System, remained dependent on PLUTO for its initial fuel supply. The undersea pipelines fed land pipelines that followed armies eastward. Fuel pumped from refineries in Britain flowed under the channel, then across France in an ever-extending network that kept pace with the advancing front. The logistics were staggering. Fuel consumed at the front came from refineries in Britain, transported by pipeline rather than by vulnerable tanker convoys. The system was efficient, reliable, and nearly immune to German interdiction. U-boats couldn't sink a pipeline. Aircraft couldn't bomb undersea pipes. The fuel supply was secure in ways that shipping never could be.
PLUTO faced challenges that engineers hadn't anticipated. The first was biological. Marine organisms colonized the pipe's exteriors, adding weight and drag. Barnacles and algae accumulated, occasionally restricting flow. The solution was periodic pressure purges, forcing water through pipelines at high pressure to scour away biological growth. The second was chemical. Seawater that leaked into damaged pipe sections contaminated fuel, creating emulsions that clogged filters and damaged engines. Engineers developed testing procedures to detect contamination and methods for purging compromised pipeline sections. The third was geological. Undersea earthquakes, small tremors common in the channel, occasionally damaged pipelines. Pressure monitoring detected these failures immediately, allowing engineers to isolate damaged sections and reroute flow through parallel lines while repairs were made. Repairs were themselves challenging. Damaged undersea pipelines couldn't be accessed for welding or patching. The solution was to abandon damaged sections and lay replacement pipes. The channel floor accumulated several miles of abandoned pipeline over the war's final year, casualties of mine strikes, anchor damage, and geological shifts. The fourth problem was success. PLUTO worked so well that demand exceeded capacity. Army logistics officers, assured of reliable fuel supply, planned operations assuming PLUTO would meet all needs. When operations temporarily outpaced pipeline capacity, shortages developed. Engineers responded by increasing pump pressures, reducing maintenance shutdowns, and accelerating construction of additional lines.
Quantifying PLUTO's impact requires understanding what would have happened without it. Traditional logistics methods, tankers, beach operations, truck transport, could have supplied perhaps 400,000 gallons daily initially, rising slowly as port facilities were repaired and expanded. PLUTO delivered over 1 million gallons daily by late 1944, 3 million gallons daily by early 1945 when the full network was operational. This additional fuel allowed operations that otherwise would have been impossible or severely delayed.
The rapid advance across France in August 1944 consumed fuel at rates that tanker logistics couldn't have sustained. Patton's Third Army advanced so quickly that supply lines stretched dangerously thin, but PLUTO kept fuel flowing. The abortive Operation Market Garden in September 1944 required massive fuel supplies moved forward rapidly. PLUTO made the logistics feasible, even though the operation itself failed for other reasons. The final drive into Germany in 1945 would have been critically fuel-limited without PLUTO. The Allied armies were now hundreds of miles from channel ports. Truck convoys carrying fuel consumed significant quantities of fuel themselves just reaching the front. Pipelines delivered fuel directly to forward areas without the self-consumption problem of truck transport. PLUTO also freed shipping for other purposes. The tanker capacity not needed for cross-channel fuel runs could support operations in the Mediterranean, carry fuel to the Pacific theater, and transport other critical supplies. Each tanker not required for channel crossings was a tanker available elsewhere. The security advantage was immeasurable. U-boats couldn't threaten PLUTO. The fuel supply was immune to the convoy battles that had characterized earlier war years. This security allowed planners to design operations assuming reliable fuel supply, without building in cushions for potential shipping losses.
Behind PLUTO's engineering triumph were people whose contributions remained secret for decades. Arthur Hartley, the engineer who pioneered HAIS pipe, received no public recognition during his lifetime. The workers who manufactured pipe, built conundrums, and operated pump stations did classified work without understanding its importance. The ship's crews who laid pipeline under German fire were performing cable-laying operations according to their official orders. They weren't told they were laying fuel pipelines. Only captains and senior officers knew the truth. Ordinary seamen thought they were laying communications cables. Dangerous work, but not as critical as their actual mission. Pump station operators worked 12-hour shifts, keeping fuel flowing, monitoring pressures, adjusting flow rates, and responding to problems. Their work was monotonous, technical, and absolutely critical. A pump failure could drain a pipeline, requiring days to refill. Operators prevented this through constant vigilance and immediate response to any anomaly. The engineers who monitored the system developed intimate knowledge of each pipeline's behavior. They learned that Pipeline 3 had slightly higher resistance than others, requiring pressure adjustment. Pipeline 7 occasionally accumulated vapor locks that needed purging. Pipeline 12 picked up more biological growth due to its route across warmer, shallower waters. This operational knowledge was personal, experiential, and largely undocumented. The engineers who possessed it were essential to PLUTO's successful operation, but left little written record. When they finally could talk about their war work decades later, many found that their achievements had been forgotten, overshadowed by more dramatic stories of combat operations. PLUTO's existence remained classified until 1949. Even then, full technical details weren't published for years. The pipelines themselves were mostly abandoned in place, too expensive to recover and not needed once the war ended. They remained on the channel floor, gradually deteriorating, eventually forgotten by everyone except marine archaeologists and divers who occasionally encounter sections. But PLUTO's technical legacy was profound. Post-war oil companies immediately saw applications for undersea pipeline technology. The first commercial undersea pipelines were laid in the Gulf of Mexico in the 1950s, using materials and methods derived directly from PLUTO. The North Sea oil boom of the 1970s required thousands of miles of undersea pipeline. Engineers designing these systems studied PLUTO documentation, learning from both its successes and failures. Modern North Sea pipelines use sophisticated materials that PLUTO engineers would envy, but the fundamental principles, flexible pipe, high-pressure pumping, continuous monitoring, trace directly to World War II innovations. Today's global energy infrastructure includes thousands of miles of undersea pipeline carrying oil and natural gas between continents. Pipelines cross the Mediterranean, the Red Sea, the Persian Gulf, and every major oil-producing region. This entire industry rests on foundations laid by British and American engineers solving a wartime crisis. The engineers who built Pluto weren't thinking about post-war commercial applications. They were solving an immediate military problem under extreme time pressure. But their solutions proved so effective that they defined underwater pipeline technology for generations. What would have happened without Pluto? This counterfactual helps illustrate its importance. Without Pluto, Allied armies would have remained dependent on tanker deliveries, beach operations, and truck transport. This would have limited fuel supply to perhaps 40% of actual consumption. Operations would have needed to be scaled back accordingly. The rapid advance across France might have stalled for weeks while logistics caught up. Patton's dramatic drives would have been impossible. His tanks would have run dry. The liberation of Paris might have been delayed. The drive to Germany's borders would have proceeded more slowly, giving Germans time to consolidate defensive positions. This delay would have had strategic consequences. A slower advance would have allowed more German forces to escape encirclement. The German army in the West would have been less thoroughly destroyed. The war might have extended into 1946, costing thousands of additional lives. Soviet forces advancing from the east would have penetrated deeper into Germany before meeting Western forces. The eventual division of Germany might have been more favorable to the Soviet Union. The entire post-war balance of power in Europe could have shifted. These are speculations, but they illustrate that Pluto wasn't merely a logistical convenience, it was a strategic enabler that allowed operations otherwise impossible. By solving the fuel supply problem, Pluto changed what armies could accomplish and thereby influenced the war's outcome.
Pluto suffers from the same problem as many logistical achievements. It's boring compared to combat operations. Popular World War II narratives focus on battles, tactics, heroism, and dramatic moments. Pipeline construction doesn't generate compelling drama. Museums display tanks and aircraft. They rarely display pipeline sections. Memorials honor combat soldiers. They rarely mention engineers who built supply systems. History books detail battles and campaigns. They give footnotes to logistics. This imbalance creates a distorted historical understanding. Wars are won by logistics as much as by combat, but public memory focuses on the dramatic and visible. Pluto moved millions of gallons of fuel across the Channel, kept armies mobile, and enabled the liberation of Western Europe. But it did so quietly, underground or underwater, out of sight, and eventually out of memory. There are no Pluto memorials in Normandy. Tourists visiting beaches walk over pipeline landing sites without knowing they exist. The pump stations that once pushed fuel across the Channel are demolished or converted to other uses. The conundrums that seemed so impressive in 1944 were scrapped for metal. A few museums preserve small sections of Pluto pipe. The Imperial War Museum in London has some, and specialized military museums include it in logistics exhibits. But these displays reach tiny audiences compared to the millions who visit combat-focused museums and memorials.
Pluto represents World War II engineering at its most ambitious and most essential. It was built to solve a problem that threatened to strangle Allied operations before they began. It succeeded beyond its designers' hopes, delivering fuel that kept armies moving at critical moments. The project required inventing new technologies, taking risks with unproven designs, and executing construction under combat conditions. Engineers solved problems nobody had faced before, working under extreme time pressure with failure not an option. The pipeline that followed the Army was more than an engineering achievement. It was a strategic weapon.
By ensuring reliable fuel supply, Pluto removed constraints that otherwise would have limited Allied operations. Armies that might have stalled for lack of fuel instead maintained momentum. Operations that seemed logistically impossible became feasible. Pluto's legacy extends far beyond World War II. Every undersea pipeline that now carries oil and gas around the world traces its lineage to those first pipes laid across the English Channel. The global energy infrastructure that powers modern civilization rests on foundations developed to fuel armies advancing across Europe in 1944-1945. The engineers, workers, and operators who built and maintained Pluto deserve recognition they rarely received. They fought the war with pumps and pipes instead of guns and tanks, but their contribution was equally vital. They solved a problem that could have cost the war, and their solution worked so well that it was taken for granted. The pipeline that followed the Army changed warfare by demonstrating that fuel could be supplied directly to advancing forces through infrastructure that followed them forward. This capability enabled mobile warfare at scales previously impossible, shortened the war, saved lives, and helped determine the post-war order in Europe. And it all began with a simple question: can we pipe fuel under the English Channel? The answer was yes, barely, with much innovation and no small amount of luck, but that yes changed history.